Alright, guys, I'm hoping with, fireworks permitting. I mean, it's the 4th of July. I want to wish you all a happy 4th of July, first of all. But second of all, who could complain about someone doing 15 minutes or a half hour of fireworks, right? The kids love to see them, you know what I mean? I'm not trying to be a jerk. But when someone's lighting off high-powered fairground-style fireworks next to your house for 2 to 3 hours, I'm sorry to say, but that begins to be a little bit overkill. So don't do that to your neighbors, all right? It's not nice. It's very startling, 2 to 3 hours of fireworks. So we're going to talk about the Big Bang. We're going to get through this. The Big Bang in cosmology is perhaps one of the most understood aspects of quantum mechanics, of general relativity, all right? But this is directly related to lambda CDM and the Standard Model. Way back, 13.8 billion years ago, the Big Bang took place. When it began, it was super dense and super hot. This was actually the Planck epoch, okay? This ended at the Planck time, where relativity is going to come into play. At 10 to the minus 43 seconds, the grand unification epoch took place, where gravity separated from the three other fundamental forces: the weak force, the strong force, and the electromagnetic force, right? So that's the first thing that happened. At 10 to the minus 37, there was inflation. Depending on who you talk to, this could either be a mustard seed to the size of a grape, or perhaps an apple, but we're just going to call it a handful of stuff. Now, I should start off by saying, scientists, the most modern, smartest scientists, think that out of everything we can see across the 93 billion light years in every direction, because of accelerated expansion, that 73% of it is dark energy, okay, which is causing the accelerated expansion. And 23% CDM, cold dark matter. You have cold dark matter, hot dark matter, warm dark matter, and baryonic matter. The 5% is the baryonic matter, and that's the part we're going to get into now. How did all that cool stuff form? The fermions, okay, the electrons, the protons, right? Well, at 10 to the minus 36 seconds, the electroweak epoch takes place, and gravity has it so that the strong force can now separate from the other fundamental forces. So now that's going to be your color charge, your gluon, your quark, passing pions back and forth, okay? Like I'm on a boat and you're on a boat, and we're on a flow toward each other. But when I pass a basketball to you, it sends you out a little bit till the flow brings you back, right? And that's how it works between gluons and quarks. They have like color charges. It's kind of like an electric charge in a way, but it's that if I'm red and you're red, we're going to repel. So you got to be different in order to fit in. And they fit in triplets. If you try to pull them apart, or sometimes if you knock particles together really hard, and it attempts to split them apart with momentum and force and all that, sometimes you'll just bring other masses into existence. It's really crazy stuff, but like at 1036, this strong force separates. And so what does that tell us for a cue about a time space? We started with something, a micro dot, right? You started to get some expansion going on, and gravity said, So you got this already tension going on between gravity and expansion. At the 1037 and 1036, your inflation and then your strong force separating. And now at 10 to the minus 12 seconds, all within microseconds, you have the electroweak and electromagnetic forces separate. And again, this strong force works really well at small distances, like a femtometer, 3 femtometers, okay? It keeps quarks and gluons together like an elastic will pull them back, right? As at about 10 to the minus 6, you now have baryons. You have the very beginning of what will become protons and neutrons, right? We still have a hot soup. We still have a ton of energy. There's still a ton of heat, right? So these things can't quite come together yet. But you're going to end up with protons and neutrons, all right? Now, about a second in, your electrons are having annihilation with positrons, and there's a remnant left over. The way it happened was, at 10 to the minus 6th, your baryonic matter, through baryogenesis, that annihilation between quarks and antiquarks, left a remnant of quarks, which became our proton and our neutron, right? As time went on, okay, about a second in, it happened again with the electron, right? And a few minutes into the Big Bang, you now had atomic nuclei. You had hydrogen, deuterium, lithium, right? And these are the building blocks that will eventually lead to the footing for the electron orbitals to take place. At about 380,000 years after, the electron now find the home on the nucleus, and you have a lot more room for photons to move around. Initially, you had a really high photon and neutrino background, a much denser background of radiation. And as our volume went up, supposedly we went from the microdot to the grain of sand size, and then to a relativistic fruit, an apple, an orange, and eventually by the end of inflation, supposedly it was about a meter across. The next really expansion we know of, we got about 10 light years across, and we already have atoms formed, right? And at that point, you started to get gases, and gases collapse, and all of that neutral hydrogen that was left over collapsed into a lot of what we think are primordial holes. The little red dots, when we look back in space, to 750 million years after the Big Bang, and you see this bright spot surrounded by red gas, they pick it up on the James Webb Mary cam and in infrared, okay, because that's the only wavelength that will show. They have something called a Lyman break, where like ultraviolet rays light rays are released when electrons will drop orbital from an N2 to an N1 and release some ultraviolet light. And then they have the Lyman break, where that's been traveling so long through neutral hydrogen that you can't see it any longer. So they call that the alpha Lyman break. Well, they also have something called inverse Compton scattering. And basically what it all boils down to is, when you have free electrons that can bounce into photons, sometimes the electrons can actually give energy to the photons, or vice versa. When you have a field, like you have a mass with atoms formed with an electron field, that's a nice flat surface for a wave to hit and bounce into, and it has all that net there. You could call it all that net, because it's all those atoms stacked together, okay, that can absorb that force. But when you got a free electron and it bounces into a photon, the photon will sometimes act like a bullet or a mass, even though it has no mass. No electric charge and no mass. But in this case, if you get a high enough velocity collision, you can actually do that. The way this happens is, a quasar will fire a proton, and it will hit the Earth's atmosphere. And when it does, it will decay into a pion and a kaon and a muon and pass through us. I think it's like every square centimeter has billions of neutrinos passing through us, but muons, they're a little more harmful than neutrinos, which are not harmful at all. But muons actually do sometimes touch stuff when they pass through them. But like something like a WZ boson, that's how they found that, because at the Hadron Collider, what they'll do is they'll use an extreme electromagnetic field to displace protons and keep them in a line and fire them relativistic, like dink, 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 millions at a time. And it will kind of paint this flash picture. Each time there's a collision, it's painting a picture for a microsecond. And so if you land enough of them, you can paint a picture for yourself for maybe a microsecond or whatever. And this is how they're able to tell things like the W and Z boson and Higgs. The W boson either has a positive or negative charge, okay, and it has a mass. The Z boson has a mass, but it has no electric charge and its own antiparticle. Just like neutrinos, you only have left, there's no right-handed. Well, with the Z boson, there's no electric charge and it's its own antiparticle. But remember where we started. We started with super hot, super dense, and the first thing we had was gravity say, I want to stay together, right? So in the next epoch, when inflation went, wow, the very next reaction was the electroweak era, where the strong force separated. So gravity, in a way, gave the strong force the ability to say, aha, stay together. And as time went on, now your electroweak and your electromagnetic force separate, and now you have separate forces going on, which enabled you to have baryons, right, left over from annihilation, electrons, right, left over from annihilation, and now fermions, electrons, and quarks, different wavelengths, right, can come together, right, and now you have atoms. The world we live in, ironically, is a very molecular, very poly-exclusion. It's a very electrical environment in terms of virtual photons back and forth, heat and thermals. Basically, solids are vibrating, liquids are swimming, and gases are flying around. This is why when you add more energy to something, it takes more volume. But with electromagnetism, that's not always true, because we know with ice ends up being a little bit less dense than water, and that's because of electromagnetism. We'll get into water one day. Water is a really miracle. To anybody that believes in the Bible, this is like right up your alley, because water is a miracle. The way it works, the way it holds together, if you learn about the electromagnetism of water, it's the most odd chance of factors that go into forming it. So for a recap, all of space, including the 73% dark energy, the 23% cold dark matter, and the 5% baryonic matter, down to 1 point, right? As this thing starts to grow at all, right, temperature is going to change on the scale, right? Because the smaller you get, the tighter things are together. So even the most little bit of expansion can change temperature a lot. Well, this is what happened. You've got 10 to the minus 43, gravity separates, 10 to the minus 37, wow, inflation, 10 to the minus 36, strong force now begins to hold baryons together, baryogenesis, the leftover quarks annihilate and leave a remnant, and gravity can do its thing to bring these strong force carriers together. And at 10 to the minus 6, you've already got proton and neutron. It's still too hot for atoms, right? But you got them there already, and at 1 second in, your electron annihilations leave leftover leptons. So you get all this leftover remnant stuff all in this now gravitational swirl, right? And you can see how that get us a ball. Each galaxy started off at maybe a meter across or whatever. And then space and galaxies and everything else you see spread out from there. Expansion, we know, goes out 93 billion light years in every direction, even though the universe is only 13.8 billion years old. So that tells you how much it's stretched. It stretched 40 some odd billion light years in every direction in 13.8. That's how far light has traveled. So we know space has grown exponentially. And they believe that the expansion, accelerated expansion, is exponential, meaning the further you go out, the faster it goes. So, and this is where I'll end off. Technically, if you go far enough out, there are galaxies moving away from us at faster than light speed. Although, in a relativistic form, if you are there in that time frame, it might not seem that way to you. But to us here, it does. Because of the speeds and magnitudes of these galaxies and the expanding space, the combination of that actually exceeds the speed of light. So, we're back to fireworks. I hope you guys have a good night. I hope you enjoyed the video. I hope it made sense. Just trying to give you some idea of how symmetry breaking phase transitions formed what we now call the universe.